Slides up here.
Oh, that's right. Let's
So our goal of doing this presentation is just to share a little bit of how we test our libraries and how we ensure that we deliver the most secure SSL and TLS solution in the world. Without further ado, we'll get started here. So today we're going to talk a little bit about the background of our company, who we are, where we came from, and what motivates us to do what we do every day. We will talk about vulnerabilities and why they matter, how testing is a mission here within our company and our culture at wolfSSL. We will give you guys an overview of the testing life cycle that we go through on a daily basis. And finally, we will cover why wolfSSL is the best, or why we think we're the best. And at the very end, I have two brief examples just showing some of the test code that we use from day to day. So this is a little bit about our history and the technologies that we offer. wolfSSL originally started out as a project at MySQL. The MySQL recognized that there was a need for a clean room implementation of SSL and TLS. They were having licensing issues with OpenSSL at the time and wanted their own solution written from scratch based on no other existing TLS solution. So our CEO, who worked for MySQL at the time, Larry Stefanik, he was tasked with coming up with this solution. And so he reached out to a former contact of his, Todd Auska, who is now the CTO and co-founder of wolfSSL. And he asked Todd if he could put something together in about 2 months. So Todd told him, sure, I can put something together. It won't be a completely full-featured solution, but yeah, we can have something up and running in 2 months. And so, yeah, SSL was written in C++ from the ground up at that time in 2004. And yeah, SSL stood for yet another SSL. Once MySQL had been using it for about 2 years, our CTO and CEO noticed that people within the hobby space and embedded systems space were starting to try and port this solution to embedded devices. And they recognized that there was a growing need in the marketplace. So they sat down and went over how can we make this even smaller, even more adaptable for embedded systems. And the solution was to rewrite the library in C rather than C++. So Todd sat down, and once again in 2006, he rewrote the entire YASL library from scratch in C, and then we called it C YASL for yet another SSL written in C. As the years progressed, MySQL did not want to keep this thing and maintain it as their own. So they gave all the intellectual property rights to Larry and Todd Auska, who then took and packaged it as its own entity, and they started branding it as wolfSSL. We did the official name change from CYASL to wolfSSL in 2014, and here we are today. So as of right now, we have 1,000+ OEM customers throughout the world, and we have 17+ resale partners. And we've grown from a company of just 3 employees in 2011 to over 30. We started out this year at 29. We're actually at about 36 right now, employees in 2018. We currently estimate that we're securing 2 billion endpoints throughout the world, and probably more than that. So these are some of the products that our company offers. We offer the SSL and TLS solution. That's our meat and potatoes of our product suite. Along with that, we offer wolfCrypt, which SSL and TLS relies on, but wolfCrypt can be built completely standalone and use just as a crypto library if you do not have a need for SSL and TLS. We also maintain and distribute a Wolf MQTT client that interops well with all existing brokers, including Azure and Amazon Web Services, two of the most popular ones. We also write and maintain our own SSH client and server. These client and servers are designed with embedded systems in mind. We've done tests where we SSH into PIC32s and various other things. And this is a embedded solution that interops with OpenSSH. We also offer the Wolf TPM library, which supports the TPM 2.0 protocol, and we are currently working on adding support for TPM 1.2, the older protocol version. We have the wolfSSL, several language wrappers. We'll just briefly cover those. We have a JNI wrapper for using our C libraries in Java programs. We have a C# wrapper for calling our C code from a C# program. We have a Python wrapper for both wolfSSL and wolfcrypt. And we have a JavaScript wrapper. Some other things of note are just the SSL proxy, secure memcached, wolfscep, secure update, and wolf command line utility. And those are all being actively developed as we speak. And most of those are in a alpha or beta type release at this moment. So our company, as people started using us throughout the world, and given that we came from MySQL, our company already had an innate open source culture built into it, and we wanted to maintain that moving forward as we broke off from MySQL and became our own entity. And to that end, we offer both a GPL v2 license library for all open source projects, and we offer commercial licensing for those of our customers that want to use our stuff in their solutions, but they don't want to open source their code. You can freely download our source code from our website or from our GitHub repository. And we offer professional support direct from any engineer within our company. If one of our engineers has worked on a specific project and you have questions, we will get you in touch with the right engineer to assist you in any of your efforts. We also offer consulting services as a company, and one of those is a quick start solution. So if you have a need to get wolfSSL up and running in a week or 2 weeks, you can leverage our engineers. We come on site, we'll do that for you, or we can do it remotely if you can provide us access to your systems. And we do various other consulting as well, including system architecture, stand-up design, etc. All of our libraries are written in the C language, and this allows for portability and ease of use. It also offers the smallest possible footprint and highest performance. All of our products are highly configurable. You can disable and enable any given feature. In fact, we like to say it's 100% modular. So if you get our wolfSSL and wolfcrypt libraries, but all you want is the SHA-1 algorithm, you can tune our library down to just provide SHA, and that's it. And you'll get a very small footprint and very good performance. We also offer performance tuning options on hundreds of different systems. We support multiple assembly optimization speedups, and we also support onboard hardware crypto whenever it's available. Our math library offers two options. We offer a stack solution, and we call this our fast math library because stuff running on the stack is much faster than stuff running out of the heap due to the overhead of mallocs and frees. But we do also offer our normal math library, which suffers the overhead of malloc and free. However, It uses only the memory it needs rather than stack solution where we have to set up static buffers large enough to handle any use case. So it does use less memory, even though you do have a performance hit. And finally, we offer single precision math on multiple devices, including ARM, and that our benchmarks to date have shown that we are beating OpenSSL on almost every system with almost every algorithm using our single precision math. We support TLS version 1.0 through 1.3. The latest implementation of 1.3 is based on draft 28, and we expect that to be the final draft. And we are currently leading the integration on TLS 1.3 in our space. We support DTLS version 1.0 and 1.2 and SSL v3 for those deprecated systems that are still using the older protocol. However, we highly recommend against use of SSL v3 in all cases if it can be avoided. We support PEM and ASN 1.1 format, through formatted certificates, including encrypted keys. We support the RSA and ECC algorithms. We have a FIPS 140-2 level 1 validation for our wolfCrypt library. So if you have a need for FIPS or are looking to sell to the government or vendors that supply the government and have a FIPS need, we can fill that need for you. We also support all NSA Suite B algorithms. And the PKCS versions listed there 1, 3, 5, 7, 8, 9, 10. And we just added support for 11 and 12. We also have a OpenSSL compatibility layer so that if your project is using OpenSSL today and you want to swap it out, but you don't want to change any of your existing API calls, we support 600 of the most commonly used OpenSSL APIs, and they all map to our wolfSSL internal functions. And if you come across an API that we don't support, we would be happy to provide an estimate for adding support for that API. Just send us a note at info@wolfSSL.com or support@wolfSSL.com anytime. So we will, as Kristen mentioned in the intro, we will be supplying these slides after. So I'm going to kind of skip through the next couple. We'll just touch on them briefly, but feel free after the presentation to go through and look if you have a need for a specific algorithm and want to see if we support it. You can check this slide here. So this lists our hashing functions, block and stream ciphers, public key support, and password-based key derivation. This is just a list of all the operating systems we have ported to today, and we are currently, if anyone in the show is in the automotive space, we're currently looking at adding support for AutoSAR, which is one of the ones we don't currently have on the list yet. These are some of the hardware crypto support solutions that we offer. So we support the AES-NI new instruction set from Intel, AVX1 and 2, vector extensions, the RD RAND and RD seed, quick assist technology. That's one we're kind of proud of, the QAT. So we've been able to achieve up to, I believe, if I recall the number correctly, 45,000 connections per second. And we've done as many as 150,000 connections in parallel. Obviously, those weren't finishing within the second, though, but it was pretty impressive. And then we also support the Intel Software Guard extensions, which is a combination hardware-software TPM type solution. For ST, we support the families listed there via the CubeMX which can generate hardware abstraction layer APIs. And that's what we support is the HAL APIs. And the HAL APIs are supported on all of these families of devices. We also support the ST-Safe TPM module, which offers 16 key slots and multiple ECC curves. And we support the Atmel's AT ECC 508A, which has 2 key slots. One is user configurable and the other is factory set. And then we support the Infineon Optega Trust TPM 2.0 module. On NXP, we support the Kinetis MMCAU and Cold Fire Sec, hardware crypto acceleration on Microsoft Azure Sphere Pluton. We have hardware crypto support. Cavian devices, Nordic devices. As far as assembly on almost all ARM-based architectures, we support assembly optimizations if you have a need there, and also on Intel chips, PowerPCs, AVR, and MIPS. And for analog devices, TI, Renesas, and we say and more. I think there's one other one we don't have on the slide deck yet, but you can see that on our website if you go look at that. And now we will get into the meat of our presentation today. So let's talk about vulnerabilities and why they matter. Vulnerabilities, as many are aware, can lead to the recovery of sensitive data. This sensitive data can be private keys, credit card information, user credentials, PII, or personal identifiable information such as street addresses, social security numbers, etc. And it can also lead to corporate secrets being lost and other bad things. This year, a report came out from CNBC. It takes them several years to gather the numbers up, but they estimated that there was around $600 billion US lost by the world collectively in all of 2016. And this number was up from 445 billion in 2014. This is trending upwards, and this is what makes us do what we do. We want to deliver the best product in the world to help users protect against this loss. So here at wolfSSL, within our culture and within every one of our engineers, testing is a mission. We have made it a mission to be the leader of the SSL and TLS pack as far as testing goes. To that end, we have 2 sets of eyes on every line of code that goes into our library. We have 0 secrets whatsoever. We make it very easy for universities, research labs, and professional analyzers and auditors to review and critique our code. We make it a mission to develop quality relationships with all of those researchers and experts within the industry that we talk to. And this helps us to deliver a world-renowned product by maintaining those relationships. We encourage and we welcome all reports. We don't care if it's coming from a student that's only been at university for 2 years or if it's a professional that's been in the industry for 20 plus years. We welcome all reports and we are always grateful. Even if a report turns out to be a false positive, we still dedicate time and effort into looking into it, and we express gratitude to the user regardless of the quality of the report. And this helps us to maintain those relationships. We maintain a perfect record of patching quicker than any other vendor in the industry. In fact, we've kept all of our patches under 48 hours anytime that a vulnerability is reported. And this quick action helps to reassure our customers and partners that we are providing the best possible solution and that they will never be affected by a 0-day attack. We will always get them a release within 48 hours of any vulnerability being reported. And oftentimes the reports aren't even public before we have our patch out, which is really good for our users to avoid those zero-day type attacks. And if a vulnerability is discovered that affects more than just our library, we are very responsible, and we don't release stuff publicly before the other vendors have time to catch up to us. And on multiple occasions, we've been asked to hold back a patch for an additional amount of time just to give those vendors time to catch up. So part of our mission is prevention through testing. So once a vulnerability has been released in the world, we immediately write test cases to reproduce it. And we run those test cases on every single commit, every pull request, everything that it goes into our master repository. And the reason we do that is because we've seen in the past some other SSL and TLS providers have suffered from reintroduction bugs, meaning they'll fix a vulnerability and then a year or two later somebody makes a change and the same bug is back in the solution again.
Caleb, we have a question. Let me see here.
Yeah.
Sarthak, I
is
think
this the same presentation that... Hello?
Go ahead.
Is this the same presentation that we attended yesterday? Or you gonna cover some other topics also in the end?
This is the same presentation that we did on Tuesday, yes.
Okay. Okay, thank you very much.
Mm-hmm. Okay. So back to preventing reintroduction into the library. So we make this part of our mission to never have the same bug appear twice. And then some of the other tests that we use to help protect us even from getting those bugs in the first place are we've developed our own in-house fuzzer, and we also, there's 3 other open source fuzzers that we use today: libfuzzer, TLS fuzzer, and American Fuzzy Lock. And we run all of those plus our own in-house fuzzer on every line of code that gets merged into our master branch. And this helps us to protect against man-in-the-middle vulnerabilities, and the sanitizers that we run help protect against smashing the stack bugs like the OpenSSL Heartbleed bug that was in OpenSSL. We do, in all of our testing, we are completely transparent. We allow our customers to review our code. We allow auditors to look at our code. We allow labs to assess our code and test it. And this, ultimately, the goal of doing that is to allow our customers to sleep as sound as a baby, knowing that the most secure, most tested solution is protecting their information. Here at wolfSSL, we are very aware that oftentimes, no matter how good your security product is, it's always susceptible to implementation bugs. And what we mean by that is a user implements our library incorrectly and doesn't use the security as it's intended to be used. And this is what leads to many breaches and hacks today. And to that end, we make it a goal. We invest hundreds of hours of critique and review into making our code very clean and very easy to work with. We also provide hundreds of examples and free pre-sales customer support. And this helps to ensure that our code is being used properly and that our customers are free from those implementation bugs. We also create tests specifically designed to protect against user input error. Anywhere that data is being passed into our library, we have sanity checks on links, on whether or not something could be a null pointer, We don't want to have users dereferencing null pointers, which can lead to crashes, which can leak sensitive information. We also have sanity checks on mallocs and frees to make sure that stuff is cleaned up correctly. And we place these sanity checks throughout the code, like I mentioned, anywhere that data is coming in that we don't know where it came from, we want to check it. So on to our testing life cycle. This is just a snapshot into the daily life of one of our developers. So we have our GitHub master repository, and one of our developers will check out a fork of the master repository when he's ready to start work for the day. And he can either develop on his own master branch or develop on a different branch. And he starts making his changes. Once the changes are in place, the developer can try to commit the code locally on his own machine. And once he does that, automatically, we have taken advantage of GitHub offers these hooks that you can place within your source code or your source code repository. And we've taken advantage of those to force a series of what we call the pre-commit tests to run as soon as the developer tries to commit locally just on their own machine. If those tests fail, then the developer fixes the issue and the cycle repeats until he gets a pass. Once all local tests have passed, then and only then is he able to push the changes up to his branch. If these tests fail, those GitHub hooks that we leverage automatically pop his changes off, so they can't even be committed until the tests are passing. Once a pull request is open, we use the GitHub webhooks to send an update to our Jenkins continuous integration server. Jenkins gets an alert that a new PR is open, and then launches a series of automated tests against the pull request. If those tests fail, then the cycle repeats. Once all automated tests from the continuous integration server have passed, only then do we assign a peer reviewer, and we'll talk a little bit more about why we've decided on this flow when we get down to the testing optimization or efficiency section of this presentation. And then once we're in the peer review cycle, again, the peer can either request changes and the cycle repeats, or the peer reviewer can approve the changes and then they're merged into our master branch. Now, every pull request is tested on its own. So at night, we want to test that all pull requests from the previous day play nicely together and don't break anything. And to that end, we launch a series of heavy hitting nightly tests that are much more, offer much more coverage and much more testing than just these automated tests that run during the pull request cycle. And if a report or if a failure is identified, a report is then sent to our testing at wolfSSL.com alias, and every developer is CC'd on that alias. And then the next morning when we come into work, if a failure has occurred, one of our developers will take ownership of the failure report and start the cycle over again. So just in recap, so we have 4 phases of our test cycle. One is the pre-commit and unit test. The second is the continuous integration testing on pull requests. The third is the peer review cycle, and the fourth is nightly testing. So for effectiveness in the pre-commit tests, we already talked about the GitHub hooks that we've leveraged to force these local commit tests to run. And the local tests cover the current configuration that the developer was working with at the time he was making his changes. So for example, if he was making changes around the triple des algorithm, he would have configured with triple des enabled, made his changes, tested his changes, and then the pre-commit test will test against that specific configuration. Then it will reconfigure the library with just a default configuration, which would disable triple des and make sure that his changes work with triple des turned off. And then finally, it'll do a full featured configuration, which turns on basically every feature within the library and make sure that his changes work with that as well. It'll also launch client and server with multiple Cypher suites to test that all the suites are working. It'll also run API and unit stress tests, which test the input to various functions, both in positive and negative ways, are being handled correctly. And lastly, it'll do some interoperability tests with external TLS solutions, such as OpenSSL and Boring SSL from Google. Once the local commit tests have passed and we're into the pull request test, these are the tests that run against each pull request. We have a series of fuzzers that run. We have static analysis checks. We have memory leak checks. We have sanitizers that catch, they also can catch memory leaks, but they catch stuff like buffer overflows and underflows. We test hundreds of different configurations for the library, including configurations that customers of ours are using today. And we do that to ensure that any changes don't break existing customer use cases. Every pull request gets tested with our FIPS library in place. It gets tested on multiple compilers, including embedded compilers, and we do cross-compiling for multiple embedded systems. And then the operating systems that are tested are, as we just mentioned, the embedded stuff. We also test on Windows, and then we test on Unix and Linux to make sure everything is working. And lastly, we have Indian tests to make sure that our little and big Indian solutions are still functioning as expected. So for effectiveness, the reason we have the peer review cycle is, one, we want 2 sets of eyes on every line of code going into our library, but 2, not every automated test can catch things such as logic fallacy. And this is just a brief example of that. So we have a pound define my test to test function, and then test function is an integer value of 3. And then we have a if condition that checks if my test is less than some variable, we're going to return an error. To a robot, this code looks fine. To an automated test, it would pass it with no issues. But then a developer, since part of our mission is to make our code easy to understand and read, a peer reviewer might look at this and say, this could be confusing. Let's go ahead and change that to keep our code readable and easy to work with. Our nightly testing is just, like I mentioned before, it's more of everything, and it touches on even some items. There are some fuzzers that run at night that don't run on pull requests. We have additional sanity checks, memory leak checks, and sanitizers that run at night. Instead of just hundreds of configurations, we run thousands of different configurations. We have multiple FIPS checks on every operating system, including embedded, Windows and Linux. We test even more compilers at night, and like I just mentioned, we continue to hit those embedded Windows, Unix, and Linux solutions. For efficiency, so as wolfSSL has grown and matured as a company, and we started setting up our test rig, we didn't have a lot of experience with it when we first started. And we've noticed several items that could be streamlined throughout our time working with creating our test rig. And so we were just going to cover some of the best practices and efficiency streamlining that we've encountered in hopes that perhaps it can help our users or customers in doing their own testing. So for the pre-commit cycle, we decided that it should never take longer than 10 minutes. And we only want to test the most frequent sources of failure. We don't want to waste time testing things that may not be a more frequent source of failure. And that's just to streamline the process and keep the time down between a developer committing code, seeing a failure, making changes, and then doing the cycle again. We also wanted these tests to be forced. We never want a developer to be able to skip this cycle because we consider it critical, and that's why we've leveraged the GitHub hooks to force those tests to run. And all of our tests have been designed with maintenance in mind. We want to be able to update our tests at any given time, and a developer that has never even looked at the tests should be able to open them up, add a test case, or remove a test case as applicable, and it should be very easy maintenance-wise. To that end, all of our tests are modular in design. All of our tests are also broken up to leverage our back-end processing systems. So this is how our system is set up here at wolfSSL. We have the Jenkins master, and then all Jenkins master does is offload tests to various systems, and then these systems report back to the master. And this keeps our master free so it never gets bogged down. And then we split up the tests on machines that are specific to a given test. Examples are we have Windows slaves, Linux slaves, slaves that just do fuzzing, slaves that just do embedded builds. We have multiple Linux slaves because we have so many configurations that we're running. If one machine gets full or has not enough random access memory to continue launching additional tests, we then offload those to another machine so that everything is more efficient and runs quicker. And then we have slaves for just testing our FIP solutions as well. The peer review cycle, as far as efficiency is concerned, there was a point in our development that we recognized the fact that the peer reviewer would see something was not working correctly, and then a few minutes later or half an hour later, the continuous integration server would report the same issue. And what this ended up doing was wasting time of our developers in doing the review when the automated tests were going to catch it anyways. So we tried to find a way to do this more efficiently, and so we've implemented a protocol here within our company that no peer reviewer can be assigned on a given pull request until all the automated tests have completed. And this was just for efficiency reasons. And then at night, when our developers go home, we wanted to make the most out of our Jenkins systems. Since we have all the slaves, we want to leverage them to their full effect. And so we have tests that run for exactly 15 hours every night from 6 p.m. to 9 a.m. And we do this so that we can continue to deliver the best tested cryptography in the world to benefit our end users. At one point, we also realized that we had reports coming in of a given failure, and say we had 3 developers that had made commits the day prior, then all 3 developers would be scrambling trying to see who broke it and which commit broke it, and this was a waste of time to have 3 developers looking at the same thing. So we implemented in all of our nightly tests what we call commit detection. And this is where if a test fails, rather than just sending an email and shutting down, the test will recognize the failure, and then it'll start backing up through all of the commits from the day prior until it identifies the first commit that's passing, and then it'll report the commit that failed, the most recently failed commit, as the source of the issue. Now, this isn't 100% accurate. We've had a few times where 2 commits were broken or didn't play nicely with other commits that went in from the day prior. And in those cases, the continuous integration server would start backing up through those commits, and it would be seeing one error, and then it would start seeing a different error, but it wouldn't recognize that the error case had changed, and so it would end up reporting only one of the commits as the source of the issue, and then we did have to do a little extra work to track down the second item. But this is being streamlined and improved every day, so our commit detection is getting better. And what this does is help us to reduce that time spent tracking down issues, and we focus all of our effort on a solution rather than just identifying the problem. And it also helps us to only involve one developer rather than multiples. And then some best practices that we do daily as we're committing code. So for every new API during the peer review cycle, this is one of the things we look for. If a developer added a new API and there isn't at least one positive and one negative test for that API, the pull request is rejected by the peer reviewer, and changes are required, and every developer has to add at least one positive and negative test for every API. The positive test would be, does it work? And the negative test would be, does it catch error cases and improper input from users? And the reason we test negatively is to help protect our users from those implementation bugs we mentioned before. So now we're going to just briefly discuss why we feel that wolfSSL is the best solution. And we think it's because we care. So our entire organization and our culture is focused on the end user and keeping our users safe. We are not motivated by external inputs. We have no investors. We're beholden to no one. And that helps us to keep our focus on the customer and not investors or the board or what they think. We're free to serve our passions in our work every day, and that's to protect the user. We also are on a mission to provide the best tested cryptography in the world, like I mentioned before. And every one of our developers is a driven self-starter. That's one of the things that we look for when we're going through the hiring process. And our concern for our customers is paramount above all else. So at the end here, like I mentioned, we just wanted to provide some brief examples, and I couldn't fit all the code onto the slides. It would have been very gross. So to make it easily readable, I've just included the basic main part of the test. So all of our automated tests are written in a common scripting language. We try to use POSIX and Bash whenever possible because all of our developers are experienced with it. And that's part of that process that keeps our tests easy to maintain. It also helps to make our tests portable so we can run them on almost any system. So this particular test configures the library with the settings for password-based support and triple DES. We can see that here. we pass in the configure options to a function in the bash script that configures the wolfSSL library with these settings. It then builds the triple des test case, which comes from our GitHub example repository, and we provided a link here. So if you guys want to go look at that afterwards, feel free to. And we have many, many tests in this repository that we run every day. And those are freely available to you guys for testing things out, exploring our library, getting familiar with it. Once the test is run, we check the result. And if the result was a failure, like I mentioned, we go into this ID commit function, which does that commit detection. And then we have this casing in the event that the bad commit wasn't able to be identified, but I don't think we've ever seen that line of code actually execute. We've always been able to find the bad commit. And then this is an example of, so we've developed our own configuration files and parsing engine that work with our client and server that are available in our downloads. You guys also will have access to that if you download our sources from our website or clone our repository from GitHub. And all these are doing is passing in which protocol version we want to launch the server with, which cipher suites, and then we set the correct certificates for that cipher suite. And this is just an example of how we're doing that. So that's everything I have. Are there any questions at this time? Please feel free to ask.
Caleb, I sent over a couple questions we had in the private message there to you.
Okay. So let's see. Let me pull up here. Yeah, I think those email questions had come in yesterday, and I did take the time to jot down some quick thoughts. So let me pull up my notes here real quick.
I'll go ahead and read the questions while you're doing that. The questions are mainly on crypto low-level implementations and related attacks that have been published in the last decade. The first one is, what generic countermeasures are implemented at crypto algorithm level that prevent from timing and cache attacks for the following algorithms: RSA signature and key generation, DH, ECDSA, ECC key generation, ECDH, AES, and DES.
Okay, so yeah, we have in our library a timing or constant time code. We call it timing resistant code because it's not 100% constant time. There are slight fluctuations on the order of microseconds, but that's just the result of software rather than hardware. So we've done timing resistance for our Tom's Fast Math and normal math libraries. And that protects the ECC and RSA solutions and any algorithm that leverages the Tom's Fast Math library against timing-based attacks. And this has been reviewed and critiqued by multiple universities and a lot of our researchers that we see every year at Black Hat, and we've always gotten positive feedback on that. As far as the cache attacks, we have blinding solutions in place, and we work with two labs, one out of France and one out of Israel, that help us to constantly check that those cache-based attacks do not work against wolfSSL. As far as ECDH, AES, and DES, not triple DES, I don't believe we've done much there. In fact, I don't know that we've ever heard of a cache or timing-based attack that works against wolfSSL where those three algorithms are concerned.
Okay, the second question was, how do wolfSSL R&D teams assess and guarantee that libraries are resistant on all supported platforms? For example, is it possible to get an exhaustive list of systematic tests that are performed internally in order to assess the security level?
Okay, so we rely on external security researchers and our customers' security teams to do the side channel analysis for us. We don't have teams here at wolfSSL actively working on that yet. Most of our employees are focused on adding new functionality and supporting existing functionality. And we do not currently have side channel analysis testing, like I mentioned, in-house, but we can work with our partners to do this analysis on specific platforms. And if any of our customers today or new customers come to us with a desired test case to implement, we will be more than happy to set that up. But we don't develop them ourselves.
Okay, thank
and
you. Are
then
there
as
any other questions?
oh, sorry. As far as the exhaustive list, trying to think, we have some documentation that describes our testing process. We posted a couple blogs on it earlier this year. We could probably send out a link for that if anyone's interested. And you know, we always are more than willing to set up a call if someone has specific concerns or want more detail too.
Okay, great. Thanks, Caleb.
Mm-hmm.
Are there any other questions from the attendees? As I said in the beginning, we will follow up with a link to the presentation as well as the slide deck. If you do have questions, feel free to send any question to info@wolfSSL.com and we'll make sure to get that answered. You've also got my email. You can reply to me directly. Well, if there are no other questions, Caleb, thank you so much for the presentation, and everyone, thank you for joining.
Yeah, my pleasure. And thank you all for joining. I appreciate it.
Have a great day.